This is your presenter, Asloob Mudassar, and I am presenting slide number 9B of the course on atomic and molecular physics. Today, I shall be covering the following topics: polar plots of Legendre polynomial, 3D visualization of spherical harmonics. You know that in the previous slide, in the slide number 9A, I have presented spherical harmonics as an angular wave function of the hydrogen atom. And the spherical harmonics was written in terms of the product of two functions. One was the associated Legendre polynomial, and the other was the factor e to the power iota m phi. So there I have separated the spherical harmonics in terms of the angular dependence of the wave function and the azimuthal dependent part of the wave function. So here I am going to give a polar plot of these Legendre polynomial, that is associated Legendre polynomial in more accurate form, and their three-dimensional visualization. And these three-dimensional visualization can be associated with the spherical harmonics, that is a complete angular part of the wave function of the hydrogen atom. So let's start. This is the polar plot of P naught. P naught means that here orbital angular momentum, or here you see that here I am talking about the quantum numbers. Here the quantum number, that is the orbital quantum number, is 0. So if you put the values of if the put the value of L is equal to 0 and also M is equal to 0 in the polynomial, in the formula of the polynomial that was given in the previous slide, you will notice that P naught as a function of cos of theta is equal to 1, and this is constant for all values of theta and phi. The plot of R, where we plot the magnitude of the associated polynomial, associated Legendre polynomial. So R is equal to mod of P naught cos of theta is equal to 1 for all values of theta, is a perfect circle of radius unity. You see that in the upper diagram, I have shown a circle of radius unity. And you know that in the polar plot, I shall be plotting 4 angles, that is 0 degree, 90 degree, 180 degree, and 270 degree. The 0 degree to 180 degree line will be referred to as the z-axis. So you see that in the previous in the slides to come, I shall not be explaining again and again that 0 degree to 180 degree is actually the z direction, and the z direction is pointed towards the 0 degree, that is upward. So we have the z direction, positive z direction along towards the 0 degree from the center, that is pointing upward, and the minus z axis will be directed from the center towards the 180 degree mark, that is directed downward. And the xy plane, or the equator plane, lies along the 90 degree and 270 degree. So this 90 degree to 270 degree line is actually a line at the center of the equator. And the 90 degree to 2, you see that here the x-axis will be represented by this line, that is the 90 degree to 270 degree line will represent both x-axis and y-axis. So in the polar coordinate, there is no other way to represent x-axis and y-axis, because this is a planar geometry and the planar representation. So both and x-axis, since they are located on the equator plane, so both x-axis and y-axis will be represented by the line from 90 degree to 270 degree. And you may assume that the nucleus is located in the center, and the other profile, for example, in this way you have the circular profile. It means that the electron is bound to follow the circular path. The electron is located away from the center at a fixed distance. Here I am plotting the fixed distance to be equal to unity. So electron is located anywhere at a distance equal to unity from the center of this nucleus, from the center of this figure, where we assume that the nucleus is centered, and the electron will be outside this spherical, this circular region in the polar coordinate system. And you know that if you also look at the x, y, and z three axes, and of course the spherical polar coordinates that we have used with the x-axis, y-axis, and z-axis coordinates, that is with the Cartesian coordinates, you will notice that the angle with the z-axis will be 0. That is, the theta will be 0 when we are talking about the positive z-axis, and theta will be 180 degree when we are talking about the 180 degree. And you know that both x-axis and y-axis in such a spherical coordinate system, three-dimensional spherical coordinate system, will be represented or will be at an angle of 90 degree and 270 degree with respect to the z-axis. And here the z-axis is also known as the quantization axis. And the equator, which is a plane which passes through the center of this region, that is through the center of this region, and also containing these two axes, that is the 90-degree axis and the 270-degree axis. That is the plane containing both x-axis, that is x-axis and y-axis, and also passing through the center of this spherical polar coordinate system is a plane which we also refer to as the equator plane. So I think that I have said enough about this polar system. So you see that in this polar system, the L is equal to 0. That is when the orbital quantum number is equal to 0. The polynomial, the Legendre polynomial represented by P0 cos of theta is equal to 1 is equal to constant will represent a circle of radius unity in the polar coordinate system as shown. But you know that if you see this polar coordinate system in terms of the actual geometry, that is the three-dimensional representation, it will represent a sphere, and the electron and the nucleus is centered in the center of this sphere. So we can say that the polar plot of R as a function of as the mod of P0 cos of theta is equal to 1 using theta as a polar angle and phi as the azimuthal angle is a sphere, and this corresponds to s orbitals. You see that here I have given the name s orbitals. These namings will become from the chemistry. So I am not going into detail of these orbitals that I shall be talking about, because they come from the chemistry, but you must remember here that the s orbital, that is the orbital which is corresponding to L is equal to 0. The spherical harmonic associated with that is a sphere of radius equal to unity when we are talking about the s orbital. And always remember that from our previous knowledge obtained from the slide number 9a, we know that the cos of theta is actually the argument of the Legendre polynomial and also the associated Legendre polynomial. And when we are talking about the Legendre polynomial, it means that we are assuming that m is equal to 0. That is, the magnetic quantum number is 0, or we do not specify the magnetic quantum number. That is, for example, in case of a P0, I have just specified as a subscript the value of the orbital quantum number L. But I have not given any value to the superscript, because superscript has not mentioned. And in the superscript, we mentioned the value of the magnetic quantum number M. So since M is not mentioned over here, we are assuming that M is equal to 0. So in the difference between the Legendre polynomial and the associated Legendre polynomial is only the difference that we do not specify the value of m in case of Legendre polynomial, but we do specify the value of m when we are talking about the associated Legendre polynomial. So associated Legendre polynomial is a more comprehensive superset, and Legendre polynomial can be obtained from the associated Legendre polynomial by just putting the value of m is equal to 0, which is the magnetic quantum number. So you see that here this will correspond, that's when L is equal to 0, the figure that will correspond is a sphere. So the electron is restricted on the surface of the sphere. It can move anywhere on the sphere, on the surface of the sphere, in case of the s orbital, or in case the orbital angular momentum of the atom is zero, or the electron is zero. So electron cannot come closer to the nucleus because it is restricted to remain on the surface of the sphere. In this particular case, when L is equal to 0. So with L is equal to 0, the wave function never crosses 0. So you see that this is the wave function in the form of a spherical shell. The wave function will never pass through the center of this region. So that's why we have said that the wave function never crosses 0. So there are 0 angular nodes. The angular nodes mean that the wave function is not going to cross the center of this region. So when it is away from the center, it means that there is no node. And you know that when we have L is equal to 0, it means that there is no node. When L is equal to 1, it means that the wave function will cross once, and when L once through the 0 value, and when L is equal to 2, the wave function will have two nodes, that it will cross twice the center of this coordinate system. And when L is equal to 3, it means that there will be 3 angular nodes, that is, the wave function will be crossing the center of this region 3 times. And you know that in this present case, we have L is equal to 0, that is, the wave function will never cross 0. So there are 0 angular nodes. The probability of finding the electron in the hydrogen atom in its ground state with L is equal to 1 depends on the distance from the nucleus and not on the direction. So you see that direction on the sphere is not important, because every part of the sphere look identical with respect to the center of the nucleus. So we can say that it depends upon the distance from the center of the nucleus, and the directions are not important when we are talking about the s orbital or the L is equal to 0 sphere. So with L is equal to 0, we have s orbital. It is a sphere in shape, and the angular nodes are 0. That is, the wave function is not crossing the center of this geometry. When L is equal to 0, we have the p orbitals. P orbitals are dumbbell in shape, and the angular nodes are 0 in that case. So when L is equal to 1, the angular nodes will be equal to 1, which means that the wave function will cross the center of this this system once. So when L is equal to 0, we talk about the d orbital, and the d orbital has a shape which is like a clover leaf. You know, the clove and clove leaf, or the torus. So this would be the shape of the d orbitals, and such a orbital will have two angular nodes. And then we shall also be talking about L is equal to 3 case, which will have the s orbitals, and we shall also discuss the shape of the s orbitals. So now let's move to the next case, in which we have L is equal to 1 and M is equal to 0. You know that when we discuss the case L is equal to 1, then the possible values of M will be 0 and plus minus 1. So 3 values of M will be possible when we are talking about L is equal to 1. So here we are talking about L is equal to 1 with the first choice that M is equal to 0. So we have P1 of cos of theta, and if you put the value of L is equal to 1 and M is equal to 0 in the formula that we have discussed in the slide number 9a, you will notice that P1 has a function P1 of cos of theta, because cos of theta is the argument of the polynomial. So P1 of cos of theta is equal to cos of theta. So this will represent the angular distribution of a pz orbital. Pz orbital means that this is an orbital which is aligned along the z-axis. And you know that we have the z-axis we have the positive z-axis from the center towards the 0 degree, and we have the negative z-axis from the center towards the 180 degree. So this axis, that is the line from 0 degree and 180 degree, is actually the z-axis. And since this pz orbital is aligned, we have given as a name it as a z pz orbital, because it is aligned along the z direction. and this again the name comes from the knowledge of chemistry. So the plot of R, and you know that we always plot the magnitude of the polynomial, because the polynomial may contain sometimes the negative signs, and you know that we cannot plot the negative signs in the polar coordinates because the radius has to be a positive quantity. So we shall always plot the magnitude of this polynomial. So we have R is equal to mod of P not cos of theta, which is equal to mod of cos theta. And this is shown in the form of a pz orbital. And you know that when we have L is equal to 1, the angular momentum will have a value which is equal to L times h bar. So in this particular case, we can say that the angular momentum has a value which is equal to 1 h bar, because 1 stands for the value of L. So L h bar, which means that 1 h bar is actually the value of the orbital angular momentum, and this is aligned along the z direction. In the next few figures, we shall not be talking about the orbital angular momentum, but we shall just be talking about the quantum numbers, orbital quantum numbers, and the magnetic quantum numbers, and the related polar representation, and also the three-dimensional representation. So you see that this plot, which is PZ plot, PZ orbital, if you look at that PZ orbital in a three-dimensional geometry, it will appear to like this one, dumbbell shape, as shown in this geometry. So this is a three-dimensional view of the PZ orbital, or you can say that it is the shape of this spherical harmonics. So let me read that M is equal to 0 means no azimuthal dependence, or you can say that phi is equal to 0. If you talk about the spherical harmonics, the full wave function of the spherical harmonics, which I have discussed in the slide number 9a, you will see that if you put M is equal to 0 over there, you will lose the azimuthal dependence, because the azimuthal dependence has a wave function which was of the form of e to the power iota m phi. So when M is equal to 0, then of course the azimuthal dependence will disappear. The shape is cylindrically symmetric around the z-axis. In 3D, the shape is dumbbell. You can see that here two dumbbells are actually shown. So this is not the this is actually one dumbbell along the z-axis. So in the three dimension, the shape is one dumbbell. One lobe points along the positive x-axis along the theta is equal to 0 direction. The other lobe points along the minus z direction, that is along the theta is equal to 180 direction. Probability of finding the electron is maximum on the z axis. So you see that if you move along the z-axis, you will see that if you go away from the x-axis, this pz orbital will have maximum value. So it means that the probability of finding the electron will be maximum along the z-axis, because there the value of the function is or the value of the wave function is larger. So the probability of finding the electron is maximum on the z-axis. As L is equal to 1, there is exactly one angular node. The node is a flat plane at the equator. So you see that this is the direction that I have shown along the z direction. So where is the equator? The equator is actually passes between the two loads. The equator is a plane which contains both x-axis and y-axis. So this plane contains both x-axis and y-axis, called the equator plane, and is passes through the center of these two lobes perpendicularly, because the z-axis is perpendicular to both x-axis and y-axis. So the xy plane is passing through the center. So there is exactly one angular mode, and the mode is a flat plane at the equator where theta is equal to 90 degree, or you can say theta is equal to 270 degree, or equator, or equivalently the xy plane. So the xy plane is actually the plane in the form of a nodal plane which passes through the mid of these dumbbell, where the value of the polynomial is 0. And you know that in the center at z is equal to 0, the value of the polynomial is 0. Because you know that our polynomial in this case it is defined as the cos of theta. And you know that when theta is equal to 90 degree, then the value of cos of theta will be equal to 0. And even when you have theta is equal to 270 degree, then cos of theta is equal to 0. So you see that at theta is equal to pi by 2 or theta is equal to 3 pi by 2, the value of the cos function is equal to 0. That is, the value of the polynomial is 0, and the value of the polynomial is 0 at the xy plane. P1 of 0 is equal to cos of theta, and Pz is aligned along the z-axis. This is what we have found. And the next thing that we shall going to discover will be that you have P1 with plus minus 1. These plus minus 1 are the values of M. That is the values of the magnetic quantum number. And this L at the subscript is the value of the orbital quantum number. So we have the value of L, which is equal to 1, and we have the values of M, which is equal to plus minus 1. These will be discussed in the next slides. And then you will see that P1 with plus minus 1 is equal to sine of theta. And then the two orbitals that we shall be talking about will be px orbital and the py orbitals. And these orbitals will be aligned along the x-axis and y-axis. And you know that when we talk about the on the polar plot, then we have no discrimination between the x-axis and y-axis, because both 90 degree to 270 degree line will represent both x-axis and y-axis. So we cannot plot separately the x-axis and y-axis cannot be shown separately on the polar plot, because polar plot is a two-dimensional plot. So let's move to the next case. Here we have the polar plot of P1 and plus 1. So the subscript is L is equal to 1 and the superscript is M is equal to plus 1. And if you substitute the value of L is equal to 1 and M is equal to plus 1 in the previous slide, in the formula on the previous slide, you will find that the associated Legendre polynomial P1 plus 1 as a function of cos of theta will be equal to minus sine of theta. And you know that sine of theta gets maximum value when theta is equal to pi by 2, that is 90 degree or 270 degree. And you know that in this case, since we always plot the magnitude of this polynomial, so the plot of R is equal to the mod of P1 plus 1 of cos of theta is equal to mod of minus sine of theta for all values of theta, which describes the theta dependence of the Px and Py orbitals. The dumbbell shape maximum occurs at theta is equal to 90 degree or 270 degree. So you may regard this one as lying along the PS direction or PY direction, because in the polar plot there is no discrimination between the x-axis and the y-axis. Both are represented by the same angles, that is at 90 degree and 270 degree. So you may consider this dumbbell to be PX dumbbell or the PY dumbbell. And the polar plot of this one is shown in over here. You know that when we talk about the three-dimensional plot, it means we take all values of azimuthal angle phi. So if you take all possible values of azimuthal angle phi, that is, you rotate this figure all around the all allowed values of azimuthal angle phi, you will see that you will get this shape. So M is equal to 0 leads to PZ orbital, as we have seen in the on page number 2, and in this page we are talking about M is equal to 1, which leads to either Px or Py orbitals, because Px or Py orbitals both will be aligned along the horizontal direction, that is along the x-axis or along the y-axis. Both directions are equivalent. And the three-dimensional is shown in over here, which is in the form of a torus or in the form of a donut. So this may be regarded as the form of a torus or the form of a. Okay, let's talk about these. Lobes are oriented along the equator, as you have seen in the two-dimensional plot. We have seen over here that the lobes are located along the equator, that is at theta is equal to 90 degree, theta is equal to 270 degree. Probability density is 0 at the poles. You see that the wave function becomes 0 in the center, that is at the z-axis. So this is actually the node where the wave function value is 0, or you can see that in the three-dimensional donut-like shape or the torus-like shape, you see that there is no signal, that is the wave function is not present in the center, because in the center there is a hole, like the hole in the form of a donut. So the lobes are oriented along the equator. Probability density is 0 at the poles, that is at the z-axis, along the z-axis, and maximum in the horizontal plane, because the lobes, as you can see, and from the torus or from the donut, you can see that along the x-axis and y direction, the value of the function is maximum. There is one polar node at theta is equal to 0 or theta is equal to 180 degree along the z-axis, because along the z-axis the function has a 0 there at theta is equal to 0, because at theta will be equal to 0 when sine theta is equal to 0. That is, there is no magnitude along the z direction. The density of the electrons concentrated around the equator, that is concentrated on the equator at the xy plane rather than at the poles. So you see that m is equal to 1 changes the orientation of the orbital angular momentum density relative to the z-axis or the quantization axis. You know that in the previous slide when we were discussing the case m is equal to 0, the maximum density was lying along the z-axis. But with the values of m is equal to 1, the density has shifted along the x direction or along the y direction. Since x-axis and y direction are you see that have the same value, so all the planes, all the other values on the xy plane are identical, because on all the at all points on the xy plane, the value of the angle will be 90 degree and 270 degree on the xy plane or at all points of the xy plane. So either we particularly talk about the either we particularly talk about the x-axis or the y-axis or any other axis on or any other angle at the xy plane, because at the whole xy plane at all points of the xy plane we have the angles which is 90 degree and 270 degree, and then of course we have this form of the torus or the donut. So we have a symmetry around the nucleus center, that is the electron is restricted, and the probability of finding the electron when we have L is equal to 1 and M is equal to plus 1 is in the form of a torus or in the form of a donut. So this is the density of finding the electron with these two particular choices of the quantum numbers, that is L is equal to 1 and M is equal to plus 1. And you can also notice the magnitude over here. That is the magnitude that I have shown in the polar plot is 1. That is, it is a circle of radius equal to 1 unit. Now we are going to discuss the next case, which we have orbital quantum number L is equal to 1, but the magnetic quantum number will be equal to -1. And you will notice that the situation is very similar to the description that I have given over here. For example, in this case. So here we are going to discuss the polar plot of P1 minus 1. Here orbital angular momentum is equal to 1 and magnetic orbital quantum number is equal to L is equal to 1 and magnetic quantum number is M is equal to -1 written as a superscript. And you know that the transformation which is used to obtain the value of minus m value of the Legendre polynomial is associated through this relationship with the Legendre polynomial on the right hand side, associated Legendre polynomial. So PL with a superscript of minus m as a function of x is related to PL as a function PLM as a function of x through this relationship. Since we have the value of PLM, that is L is equal to 1 and M is equal to 1 from the previous slide, which was equal to minus sine of theta. You can see over here. So substituting this function on the right hand side and using the value of L and M, you can find out the value of this function. That is PL and minus M. So using L is equal to 1 and M is equal to 1 in this formula will give you this value, that is P1 minus 1, or as a function of cos of theta is equal to half that of sine of theta. And you know that again sine appears over here. And if you will notice that this is the circle, but it has a radius which has a magnitude equal to 0.5, because 1 over 2 factor of half is appearing in this polynomial. So if you plot this one, you have to plot it in a radius equal to half unit. And again, you see that we have sine theta, which means that the function is maximized along the 90° and 270°. So you have the dumbbell plotted along either the x-axis or the y-axis without discrimination. So you may assume this dumbbell on the whole xy plane for when we rotate it with values of phi. So with all possible values of phi, this will appear to be like the form of a donut or a torus as shown in this figure. But you know that here in this particular case, as I mentioned you, the value of the radius is 0.5, whereas in the previous case, the value of the radius was equal to 1. But you know that the probability of finding the electron in both of these cases will be equal to 1, because the probability density will depend upon the value of absolute square of YLM, where YLM are the spherical wave function. And you know that since this is the plot, three-dimensional plot is a plot of the spherical harmonics, so you will notice that if you plot the absolute value of spherical harmonics for the previous case and for the present case, where the magnitude is 1 and 0.1 respectively, but the probability will be the same, because in the spherical harmonics, when you plot the absolute square of the spherical harmonics, the normalization constant that appears will adjust itself in such a way that the probability for the two cases will be identical. That is the probability of finding the electron in this donut type shape or in this torus type shape for the magnetic quantum number +1 and for the magnetic quantum number -1 will be identical, will be the same. So the probability density, which is given as the absolute square of the spherical harmonic function, is the same for both signs of m is equal to +-1, because the normalization constant will take care of this probability density to be equal. It has two circular lobes centered along the equator plane, as we have shown in the polar diagram. That is, the two lobes are oriented at theta is equal to 90° or theta is equal to 270°, which is the same as for the case of m is equal to 1. The probability density is 0 at the poles, because you see that the function vanishes in the center. As you can see from the both plots, that is from the polar plot and also from this donut shape plot, the function is not appearing in the center and the value of the function in the center is 0. That's why we say that the probability density is 0 at the poles, that is along the z-axis, and maximum in the horizontal direction, or maximum along the x-axis, or maximum along the y-axis, or if we talk about the this donut shape, that is, we can say that maximum on the xy plane. There is one polar node at the theta is equal to 0 or theta is equal to 180°, that is along the z-axis. At theta is equal to 0, the function sine of theta is equal to 0, because sine of theta is equal to 0, which means that there is no magnitude along the z direction. The maximum magnitude is 0.5, which is half that of the m is equal to 1 case. In spherical harmonics, which is given by the YLM, which is written as YLM, and the probability density is given by the absolute square of YLM for the value of L and M. You will notice that in spherical harmonics, the normalization constants usually equalizes the magnitudes, and the probability densities for the two cases, that is with M +-1, will be identical, will be the same. So you see that here up till now we have discussed two cases. L is equal to 1 and there were two choices available to us with the m is equal to plus minus 1. And we have noticed two things over here. That is either we have the bundle along the z direction or dumbbell along the z direction, or we have the dumbbells on the xy plane, that is with the m plus 1 and also with the m is equal to minus 1, the dumbbell is on the xy plane, forming the shape of a donut or the shape of a torus in both cases. That is m is equal to plus minus 1, both have the same identical cases. The magnitudes, however, are different. The magnitude is 0.5 in the case of m is equal to minus 1, and the magnitude of the circular region plotted in the polar coordinate system is m is equal to plus 1, whereas this shape is only aligned along the z axis. Now the next case I have, so these are the dumbbell shaped, and the three possible shapes will be PZ shape, which is in this case, PX or PY shape in this case, and again PX or PY shape in this case. Now we are going to discuss P20. Here we are assuming that the value of the orbital quantum number is 2 and the value of the magnetic quantum number is 0. So L is equal to 2 and M is equal to 0. So we are now going to discuss the plot of P2 of 0, and if you substitute value of L is equal to 2, M is equal to 0 in the formula discussed on slide number 9a, you will find that the polynomial has this value. So P20 as a function of cos of theta is equal to half times, within the parentheses we have 3 cos square theta minus 1. So L is equal to 2, M is equal to 0 has a significant density at the poles with M is equal to 0. So this is the case, M is equal to 0 is shown. And you see that we have the maximum density along the Z direction. That is we have the dumbbells occurring along the Z direction, slightly bit elongated, and we have also a pair of dumbbells also. So let's read the text first and then I explain. So L is equal to 0, M is equal to 0 has a significant density at the poles, but when M is equal to plus minus 2, which we shall be discussing in the next 2 pages, the density shifts from the Z axis towards the equator. So with M is equal to 0, the density is aligned, the max density is maximum along the Z direction. And later in the next 2 cases where we are going to discuss M is equal to plus minus 2, you will see that the density will be shifted from the Z axis towards the equator, that is along the XY plane. This is a 3-dimensional picture is also shown over here. The angular distribution of a P20 cos of theta corresponds to dz square orbital in hydrogen atom. So you see that this shape in chemistry is referred to as the dz square orbital. dz square orbital. Okay, so you see that here now nodal points corresponding to P20 of cos of theta is equal to 0, because in the center you will see that the wave function has a 0 value. For example, in the polar plot you can see that in the center the wave function has 0 value. So the nodal occurs. So this function has a 0 value over here in the center. But to approach this 0 value, the nodal points corresponding to this P2 of 0 to be equal to 0 gives 2 values of theta. That is at theta is equal to 54.7 degree and at a value of theta is equal to 125.3 degree, which is actually the same line. If you join these two angles, you will get the same line, and this same line is actually giving you the value of the function to be equal to 0. So there is one line corresponding to 52.54.7, and there is another line which is at an angle of 125.3 degree. So these are the two lines which will pass separately towards through the center of this picture, or through the center of this wave function, where the wave function is 0. So there are two nodes actually. So you see that these canonical nodes are characteristics of the dz square orbital. So when we talk about the polar plane, for example this plane, we find out the two angles at which we can find out the density of the function to be is 0. One is the line which is drawn at an angle 54.7 degree. So if you draw a line at an angle of 54.7 degree, that will pass through the center of this picture, and the other angle is 125.3 degree, probably over here. So if you draw this line, it will pass through the center of this picture. So these two lines, that is theta is equal to 54.7 degree and theta is equal to 125.3 degree, will represent two nodal lines passing through the center of this wave function. But you know that if you consider this one in a three-dimensional picture, then of course the nodes will become canonical nodes. So then these two lines which I have discussed as different lines, these lines will appear as the conical nodes, are the characteristics of the dz square orbital. So you can see that many lines will be passing around this shape, passing through this function, passing through this donut or the torus function, and approaching to the center of this wave function, where the wave function is 0. So this shape in chemistry is referred to as the dz square orbital. And when we talk about the polar figure, we notice that there are only two nodes, one at 54.7 degree, the other is at 125.3 degree in this polar picture. But if you talk about the three-dimensional picture, you will notice that these will be referred to as the conical nodes, and these are the characteristics of the dz square orbital. So you see that many lines then would be able to pass through the center of this wave function, that is will pass through the center of this donut or the center of this torus. Two large vertical lobes point along the z-axis. Two smaller lobes represent a donut or a torus and surround the center. Maximum probability occurs along the z direction, that is along the theta is equal to 0 or theta is equal to pi direction. The maximum probability exists at along the z-axis, along the two large lobes, and you still have a donut, because you see that in the three-dimensional shape you change the angle from 0 to 2 pi, that is the phi angle, and then of course this figure, that is the figure shown in the above polar figure, is rotated, and of course this picture is formed, which is referred to as the dz square orbital. That is the shape of the dz square orbital. So you see that, and you can also find out these angles from this formula, from this polynomial. Put this value equal to 0, that is half, and within the parenthesis you have 3 cos square theta minus 1. Put this expression equal to 0, and then finally you will get 3 cos square minus 1 equal to 0. You will get 3 cos square is equal to 1. You will get 3 cos square is equal to 1 over 3. You will get cos theta is equal to plus minus square root of 1 over 3. And then of course you will get theta is equal to cos inverse of square root plus minus times the square root of 1 over 3, and solving that one you will get two values of theta. One will give you a value of 57.54.7 degree. The other will give you the value of 125.3 degree. These two values will correspond to the nodal lines which will pass through the center of this picture, that is the polar picture. Now you see that we are going to move to the next case. Here we have discussed the m is equal to 0 case. Now we are going to discuss the other two cases, which is m is equal to plus 2 case and m is equal to minus 2 case. So with m is equal to 0 case, remember the name of the picture is, this orbital will be referred to as the dz square orbital. Now this is the case when we have the value of m, that is the magnetic quantum number, equal to plus 1. And here we are going to plot the function r is equal to the plot of mod of p21 as a function of cos of theta. And this p21 as a function of cos of theta is equal to minus 3 cos of theta sine of theta. This can be obtained by putting the value of L is equal to 2 and M is equal to plus 1 in the formula given on slide number 9a. You will find out the polynomial to be equal to this. And this polynomial can also be written in the form of minus 1.5 times sine of 2 theta. And you know that here you will find the two pair of lobes. One pair of lobe is located in the xz plane and the other is located in the yz plane. So you see that the equator plane is actually the xy plane. This 90 degree to 270 degree contains both x-axis and y-axis. And the z-axis is from the center to 0 degree. So the vertical direction is the z direction, and both 90 degree and the 270 degree will represent the x direction and the y direction. So the 90 degree to 270 degree actually is the equator plane containing both x-axis and y-axis. Then these dumbbells, these pair of dumbbells, for example, this dumbbell will now be lying on the xz plane, the other will be lying on the yz plane. So the angular distribution of a P21 of cos of theta corresponds to the dxz and dyz orbital in the hydrogen atom, because they are neither located on the equator plane nor they are located along the z-axis. So they are located in the xz plane and also in the yz plane. One pair of lobes is located in the xz plane, the other pair of lobes is located in the yz plane. So that is why the orbitals are named as dxz and dyz orbitals. And you see that the magnitude of this orbital is equal to 1.5. This is the magnitude of the circle in which these two lobes, these two set of lobes have been plotted. So the maximum magnitude of 1.5 occurs where the maximum probability occurs. That is at theta is equal to 45 degree, at 135 degree, at 225 degree, at 315 degree. So these are the points along which the lobes will be aligned. For example, these two lobes, this set of lobes is aligned at an angle of 45 degree and at 225 degree, because they are shown with the same color, red color, 45 degree and 225 degree. This is one pair of lobes. And the other pair of lobes is located at 135 degree and 315 degree, shown in green. So you see that these are the two lobes which we have shown in the polar coordinates, but actually these are in the three-dimensional geometry. If you look at the three-dimensional XYZ geometry combined with the spherical polar coordinates, you will see that these one set of lobes is located in the XZ plane, and the other will be located in the YZ plane. That's why these orbitals are called the dxz and dyz orbitals. The three-dimensional picture, when we rotate the angle of a phi from 0 to 2 pi degree, then of course these lobes will be rotated about the z-axis and you will have a shape like this. three-dimensional shapes are shown. The nodal points, one due to sine of theta. You know that if you consider the polynomial, for example, if you consider the polynomial in the form of the product of these two functions, that is equal to minus 3 times cos of theta sine of theta. So you can find out the two nodes. One node will be provided by sine of theta, the other node will be provided by cos of theta. The node sine of theta will be equal to 0 at one set of values, that is at a value of theta is equal to 0 degree and theta is equal to 1 of degree 180 degree, sine theta will be equal to 0, and cos function will be equal to 0 at theta is equal to pi by 2 and theta is equal to 270 degree. So two nodal points, one due to sine of theta is equal to 0 along the z-axis, that is along the theta is equal to 0 degree and 180 degree, and the second nodal point will be due to cos of theta is equal to 0, which will give you an angle at theta is equal to 90 degree and theta is equal to 270 degree at the xy plane, that is at the equator plane along the x-axis or the y-axis. Because you know that in the polar coordinate there is no discrimination of the x-axis or the y-axis on the xy plane or on the equator plane, because these two axes will be identical. So m is equal to 1 represents a transition between the polar heavy case m is equal to 0. So you know that m is equal to 0 case is the polar heavy case. What does that mean? We have discussed in the previous figure the case of m is equal to 0. So this is the polar heavy case. That is, we have a high density along the pole, that is along the z-axis. That's why it is called a polar heavy case. So m is equal to 0 case is the polar heavy case. And here we are discussing m is equal to 1. And we shall notice later on in the next 2 to 3 pages, that when we shall discuss the m is equal to 2 case, we shall call this case as an equator heavy case. So let me show you that case also before I discuss. For example, this is the equator heavy case, because this is lying along the equator plane. So these two cases are along the equator. So m is equal to plus minus 2 is the equator heavy case, because these two bundles are lying along the equator. But you know that this is in the intermediate range, that is at some angles, not lying in the equator, not lying along the pole, but in the region that is lying along the xz plane and yz plane. So that's why we say that m is equal to 1, that is this present case represents a transition between the polar heavy case m is equal to 0 in the previous slide and the equator heavy case, which will be m is equal to 2 case we shall be discussing next. So m is equal to 1 avoids both the poles and the equator, and the density lies in the diagonal quadrant. So you can see that the density lies in the quadrants. So this was the case that we have discussed, is P is L is equal to 2 and M is equal to plus 1. And you can notice the magnitude was equal to 1.5. Now next we are going to discuss the case P is equal to 2 and M is equal to minus 1. For example, this case. In this case we are going to plot orbital quantum number L is equal to 2 and the magnetic quantum number M is equal to minus 1. So this is the polar plot of R is equal to mod of P2 minus 1 as a function of cos of theta. And if you plug in the value of L is equal to 2, M is equal to minus 1 in the formula discussed in slide number 9a, you will notice that P2 minus 1 cos of theta will be equal to half times sine of theta cos of theta. And if you combine sine of theta cos of theta, you will get is equal to 0.25 sine of 2 theta. And again, you see that as discussed in the previous case, you have the same two lobes aligned along the quadrants, that is in the xz plane and in the yz plane. This description is very clear and identical to the same as discussed in the previous case. That is for the L is equal to 2 and M is equal to plus 1 case. The same is the description. The only difference is that the magnitude is 0.25 over here. And you see that in the previous case, the magnitude was equal to 1.5. The only difference is that of the magnitude. The rest of the description is the same. Again, this will appear you like that of the clover leaf. If you look at the shape of the clove, it will appear to as the clover leaf shape function. So with m is equal to 1, you have 4 equal lobes or 2 pair of lobes. And again, the description that I have discussed in the previous slide will also be applicable to this figure. Again, the angular geometry is the same for both m is equal to plus minus 1. The geometry is the same for m is equal to plus 1 and m is equal to minus 1. And m is equal to plus 1 case has been discussed with much greater detail. But only the difference is that the magnitude in this case is only 0.25, which is 1/6 times the magnitude discussed in the previous case. So the angular distribution is identical to m is equal to 1 case. However, the magnitudes are scaled down by a factor of 1/6 compared with P21. The normalization constant for P21 and P2 minus 1 are, however, different, have different values and ensure consistent probability. So nodes are also identical to P21. So you see that the probability density, since the pictures are the same, the nodes are also identical. And the probability density is also the same. Don't bother about the value of the function. That is, the value of the function is very small over here, 1/6 times the value as discussed in the previous case. So it is only 0.25. Don't consider this a small value, because the normalization constant will take care of this factor, and the probability density would be the same for both m is equal to plus 1 and m is equal to minus 1 cases. The shapes are identical. The probability densities are identical. The number of nodes are also identical. For the m is equal to minus 1 case to that of the m is equal to plus 1 case. Now you see that we are going to discuss L is equal to 2 and m is equal to plus 2. So if you put the values of L is equal to 2 and m is equal to plus 2 in the previous formula, you will notice that this is the value of the polynomial P22 of cos of theta is equal to 3 sine square theta. Now you see that here the density is concentrated, is lying along the x-axis, is lying along the xy plane. You see that I have shown it to be along the x-axis. But you know that actually this is lying on the xy plane, because I told you that the xy plane contains both x-axis and y-axis, and there is no discrimination when we are talking about the 90° to 270°, because this contains the equator plane, and the equator plane contains both x-axis and y-axis, and of course the equator plane is also known as the xy plane. The angular distribution of this P22 of cos of theta corresponds to the two orbitals dxy and the dx square minus y square orbitals. So these are the two orbitals which are associated with such a figure which is lying on the when it is lying on the xy plane. This bundle is lying on the x plane, y plane. We refer to as this as a dxy orbital. And when this is aligned either along the x-axis or along the y-axis, this is referred to as the dx square minus dy square orbital. So you see that I am not going to discuss dxy and dx square minus y square in greater detail, because these are the orbitals concerned in chemistry. For the angular distribution of a P2 of cos of theta corresponds to dxy or the dx square minus y square orbitals in the hydrogen atom. The shape has two broad rounded lobes which meet at the origin. So you see that at the origin the wave function has a zero value. That is the point of it is the nodal point over here where the wave function is zero. And you also know that the wave function contains that is the polynomial contains a sine square, and you know that this sine square vanishes when theta is equal to 0 degree or theta is equal to 180 degree, because at that point the sine function has a zero value. So theta is equal to 0 degree and theta is equal to 1 degree will give you the value of the nodes. In the 3D plot, the 3D plot would look like a fat donut or a torus. Because we have to rotate this figure for the direction of 2 pi from 0 to 2 pi, and then of course when these lobes are rotated in the dx or dy lying in the dx and dy plane, when these are rotated about the quantization axis, that is about the z axis, then of course then we find out this fat donut type shape or a torus type shape. And these dumbbell shapes lying in the xy plane is referred to as the dxy plane, dxy orbital, or lying along the x-axis, for example along the x-axis or the y-axis, then these are called dx square minus dy square orbitals. The density is entirely concentrated at the equator. So since these shapes are lying along the are lying on the equator, so of course the density is maximum in the equator plane. And the equator plane, you see that it passes is the plane located at an angle of theta is equal to 90 degree and theta is equal to 290 degree. Is the plane which is the equator plane, and the equator plane you know that contains the x-axis, contains the y-axis, contains and also labeled as the xy plane. This gives the electron density in the xy plane for a d orbital, and these d orbitals are referred to as the dxy orbital or the dx square minus y square orbitals. There is a double angular mode. So you see that when n is equal to 2, we have the double angular mode located at the center of the z axis at theta is equal to 0 degree and theta is equal to 180 degree. For m is equal to 0, and you see that these are the two modes which are coincident with each other. For m is equal to 0 state, dz square points primarily along the z axis. This is what we have seen. Dz square orbital is what we have seen. So let me show you again. This is dz square orbital. And you see that these are the orbitals not on the xy plane, or neither along the xy plane nor along the z axis. These are in the dxy, these are the dxy or dyz orbitals. And this is the orbital that is the dxy or dx square minus y square orbitals. So you can see that for m is equal to 0 state, the dz square points primarily along the z axis. M is equal to 2 case points entirely away from it, that is on the xy plane. So m2 case have a density, angular density on the xy plane. Note a shift of electron density from the poles, that is from the z axis to the equator xy plane. So when we were restricted on the m is equal to 0 plane, the mode density, the electron density was maximum along the pole, that is along the z-axis, as we have seen in the case of dz square orbital, that is in the case of m is equal to 0. And in the case of m is equal to plus minus 1, we have seen that our density lies in the xz plane or yz plane. And in the m is equal to 2 case, m is equal to plus 2 case, we have seen that the density lies on the equator plane. And these and the resulting orbitals, we have given them the name as dxy, dxy orbital or the dx square minus y square orbitals. Next, we are going to discuss the negative m is equal to minus 2 case. So in the next case, L will be equal to 2, but m will be equal to minus 2. Here you can notice that the magnitude is 3. And in the next shape, with the change of the quantum number minus 2 to minus 2, the shapes will be identical. All the things will be identical, on the magnitude will be smaller. You will see here the magnitude is just 0.125. Very much smaller, and the wave function has that is the polynomial, the associated Legendre polynomial for L is equal to m is equal to minus 2 has a value equal to 1 over 8 times sine square theta. And in the previous case, for m is equal to plus 2, you will see that the value was equal to 3 times sine square theta, and here the value is 1 over 3 times sine square theta. Since sine square appear in both these functions, so all the rest of the parameters will be the same. The shapes will be the same, the nodes will be the same, the three-dimensional shape will also be the same, and the electron density will also be identical. Only the difference is that the magnitude is smaller. You can see that the magnitude is just 0.25 over here. The rest of the discussion will be the same as we have discussed over here in the case of m is equal to plus 2. So in the case of m is equal to minus 2, the same explanation will be applicable. So I am not going to discuss that one. Only I am going to discuss some critical points. So P2 minus 2 is a scaled down version by a factor of 1 over 24 compared to P22. The actual probability in the two cases, which is given by the absolute square of the spherical harmonics, that is absolute square of y2 minus 2 and the absolute square of y2 plus 2 is the same, because the normalization constants with these harmonics will take care of the probability density will be the same, and irrespective of the small magnitude of these density functions over here, which is just 0.25. That is, the wave function is restricted in this region. Summary: m is equal to 2 exists along the poles, that is along the z-axis, where we have the orbital named as dz square with a central donut. With m is equal to plus minus 1, there were 4 lobed clover leaf or 2 set of lobes at an angle of 45 degree or 135 degree and lying in the xz and yz plane, and the resulting orbitals were called dxz or dyz orbitals. And then in these last two cases, we have m is equal to plus minus 2. These are where the electron density is concentrated at the equator, that is in the xy plane. So with m is equal to 0, we were in the along the z-axis, and the density has shifted to the xy plane with the values of m is equal to plus minus 2. Now you see that we are going to discuss the case when the orbital quantum number is 3. So this is L is equal to 3 and m is equal to 0. So if you use L is equal to 3, m is equal to 0 in the previous formula on slide number 9a, you will find that the polynomial has a value which is equal to half times the, within the parentheses we have 5 cos to the power 3, cos of theta to the power 3 minus 3 times cos of theta. This is the value of the polynomial, and the resulting polar plot is shown. In the polar plot, you can see the shape, and the magnitude of this polar plot is restricted in the region of 1. And let me explain that it corresponds to a shape, that is the three-dimensional shape. That is the three-dimensional shape of this one is referred to as, for example, this shape is referred to as the fz cube orbital. So this is the fz cube orbital. So let me read the main features of this. So this is the fz cube orbital, because when we talk about L is equal to 3, it means that we are talking about the f orbital. So we are since we are talking about the value of orbital quantum number L is equal to 3, so we are talking about the f orbitals. And here in this particular case, we are talking about the magnetic quantum number to be equal to 0. So this corresponds to, that is the three-dimensional picture of this one corresponds to fz cube orbital in hydrogen atom. This plot is a six-lobed structure, or you can assume that it has three pair of lobes. Two prominent lobes are along the z-axis, or you can say one pair of a prominent lobe is located along the z-axis, and four smaller lobes are branching out of it one, or you can say that two set of smaller lobes are branching out of it. Maximum probability is concentrated along the z-axis because the lobe have a maximum magnitude in that direction along the pole. So the maximum probability is concentrated along the pole or along the z-axis. Since we are talking about L is equal to 3, so there must be three angular nodes. So there are three angular nodes, canonical plus planar. Planar means that the plane xy will pass through this figure, through the center of this figure. So let me explain a little bit about the figure. The upper two lobes, that is this lobe and this lobe, if these two lobes are rotated about the z-axis, because we have to change the angle phi from 0 to 2 pi, so these two lobes will be rotated and the upper donut will be formed. And when these lower two lobes below the xy plane, when these are rotated, then of course the lower donut will be formed. So two donuts will be formed due to these smaller lobes. There are three angular nodes, canonical plus planar. Planar means xy plane is passing through the center between these two these two donuts. Xy plane exists where the value of the z-axis is 0. So that xy plane will form one node. The other nodes will come from the canonical, and these will come at some angle that is at 39.2 degree, and at one line will pass at 39.2 degree, the other line will pass through the z is equal to 0 at 140.8 degree. And these two lines can be obtained when you set the value of this function to be equal to 0. That is, if you take cos of theta common from this parenthesis, then cos of theta that will be equal to 0 on the xy plane. So one nodal plane is the nodal plane, is the xy plane, and then you are left with the 5 cos square theta minus 3. And if you solve this equation, if you set 5 cos square theta minus 3 equal to 0, you will get the two values of theta. That is theta is equal to 39.2 degree. This is one line that will pass through z is equal to 0, and the other line at 140.8 degree that will pass through z is equal to 0, and these two lines are obtained by setting 5 cos square theta minus 3 equal to 0. So let me read again quickly. There are three angular nodes, canonical, that is at some angles other than the axis angle, other than the angle that is shown in the polar picture. So there are three angular nodes, canonical plus planar, where the probability is 0, or where the function is 0. One is at theta is equal to pi by 2, that is on the xy plane, and the other two at theta is equal to 39.2 degree and 140.8 degrees. So this is what we have covered. L is equal to 3 case and M is equal to 0 case. And the picture is referred to as the FZ cube orbital. So this is the FZ cube orbital. The name comes from chemistry. So you see that this is the electron distribution, angular distribution of the electron. When the electron is in this state, it has a distribution like this one. So you can find out the probability of the electron existing in this orbital, which is given by its three-dimensional demonstration. Okay, the next case that we are going to discuss is L is equal to 3 and M is equal to +1. And if you put these values in the polynomial, you will get the polynomial has this expression. That is P31 has an expression equal to -3/2 sine of theta. And then we have the parenthesis which contains the 5 cos square theta minus 1. So you see that there are three distinct pair of lobes. That is one pair of lobe, two pair of lobe, three pair of lobe. So mistakenly, I think that I have written 4 distinct pair of lobes. Actually, these are the 3 distinct pair of lobes in this picture. So you can make a correction over here. So distribution is 0 at the poles. You see that all these lobes meet at z is equal to 0. So it means that this provides one nodal point where the wave function vanishes. So distribution is 0 at the poles, that is at z is equal to 0, and the density peaks at specific angles between the axes. So you see that at these, the density is maximum along these lobes. And if you rotate this figure along the z-axis for all values of, for all allowed values of phi from 0 to 2 pi, you will get the three-dimensional picture shown over here. So the two-dimensional 2D projection shows 4 distinct pairs. So here not the 4 but the 3 distinct pairs of lobes. Distribution is 0 at the poles and density peaks at specific angles between the axes. 3 sets of angular nodes at the poles where z-axis passes at theta is equal to 0, theta is equal to pi, because sine of theta is equal to 0 and the sine of theta is only 0 when theta is equal to 0 or pi. Others at theta is equal to 63.4 degree, 116.6 degree due to 5 cos square theta minus 1. So the other for the other 2 nodes exist at these angles. That is the line at theta is equal to 63.4 degree will pass through the z-axis, where the z-axis has 0 value, and 116.6 degree line will also pass through z is equal to 0 line, providing 3 values of nodes. Theta is equal to 0, theta is equal to 63.4, and theta is equal to 116.6 degree. And these 2 points can be obtained from by setting a 5 cos square theta minus 1 equal to 0. The increased number of lobes and nodes corresponds to higher kinetic energy associated with higher angular momentum. So since we are using L is equal to 3, it means that the corresponding L is equal to 3 is the orbital quantum number, and the associated angular momentum with that quantum number, which we refer to as the orbital angular momentum, will also be high. So this corresponds to higher kinetic energy of the associated and also associated with the higher value of the orbital angular momentum. Complex spatial quantization is associated with f orbitals. So you see that here we have talked about the f orbital, which is the okay, this is, you see that the complex orbitals having 3 pair of lobes, and the density is shown in 3 dimensions over here. This has 3 nodes. The nodes angles have also been given, and the electron density is obvious from the nodes from this 3-dimensional picture. So you can find out the probability, and you can also notice the magnitude of this one. That is, the wave function is constrained in a radius of 2 units. And these small lobes, which actually form a donut, is restricted to a region of 1.5. whereas the main lobes are restricted to the region of 2 radius equal to 2 units. Now the next one is we are going to discuss the case of orbital L is equal to 3 and M is equal to -1. But for that one, you will see that the similar description will appear, only the difference will that the magnitudes will be different. So let me show you the next case. This is the next case where we have the orbital quantum number L is equal to 3, but the magnetic quantum number is equal to -1. And you know that this function is very much the same as the previous case. Is it exactly same, or there is a difference between them? You can see that there is a negative sign over here, and also the magnitude is different. Here the magnitude is 3/2, which is equal to 1.5 for the internal lobes, for the small lobes, but here you can see that it is 1/8. The rest of the picture, the shape of the pictures in the polar coordinates and in the three-dimensional coordinates is the same. So the discussion is also the same. Only you can notice that the magnitudes are different. That is, the main lobes are restricted to lie within the radius of 0.166, and the smaller lobes are restricted in the region of radius equal to 0.125. The rest of the discussion is the same. Number of nodes are the same, which are 3 in number, and the electron density is also the same. The probability would also be the same, because in the probability the normalization constant will take care of these magnitude of these smaller magnitudes, but the probability density will be the same. So let me read this important one. The rest of the description is similar to the P31 case. The values are scaled down significantly by a factor of 1/12. The probability density is the same in two cases, which is given by the absolute square of y31 and absolute square of y31, which are the harmonics, and y functions are the spherical harmonics. And the normalization constant with these one will take care of the normalization, and the probability will be taken care of the normalization constants which are used with these spherical harmonics. So you see that the shapes are identical, only the magnitudes were different, and the magnitudes will be taken care of by the electron density, or by the probability density of the electron, which will be taken care by the normalization constants used with the spherical harmonics. The next case that we are going to discuss is the case of a magnetic quantum number equal to +2. So this is the case where we have the orbital quantum number L is equal to 3, but the magnetic quantum number is M is equal to 2. And the polynomial, the associated Legendre polynomial has a value equal to 15 sine square theta into cos of theta. You can see these lobes, the magnitude is 6. And this component can be used to construct F orbitals like Fz times x square minus y square, or f x y z. So these two type of orbitals can be constructed with this simple orbital, because you can combine a chain of orbitals to construct these orbitals, as this is the case of molecular bonding. Comes from the knowledge of the chemistry, but I am not going to discuss that one. So just talking about that, these orbitals will combine to give you that is, you can form Fz times x square minus y square orbitals, or you can also construct f of x, y, z orbitals using this, or combining this simple orbitals, which is the F3 2 orbitals. So again, you see that these are not lying on the equator plane, nor they are lying along the pole, that's along the z-axis. So they are neither lying along the z-axis, nor they are lying along the xy plane. So they are lying at some angles. The three-dimensional picture is also shown. The plot shows clover leaf like structure with 4 distinct lobes, or you can see that 2 pair of lobes, and the lobes are restricted in a region of radius equal to 6. Structure is similar to the case L is equal to 2, M is equal to 1, but differs in intensity and constraints. Of course, there are constraints on the amplitudes which are different from the previous case, and the intensity values will also be different from the previous case, which was the L is equal to 2, M is equal to 1 case. So density peak occurs at these values, 54.7 degree and 125.3 degree. That is, the lines that you will draw at this angle will pass through Z is equal to 0 and also through the x-axis, that is at x is equal to 0, y is equal to 0, z is equal to 0, and at and the line which is drawn at an angle of 125.3 that line will also pass through z is equal to 0. So there are 3 angular nodes. One is through the z-axis, that is through the pole, and the other through these 2 angles. One at the equator, that is at theta is equal to 90 degree, along theta is equal to 90 degree. That is one along the x-axis, that is on the xy plane, and the other because cos of theta is equal to 0 on the xy plane. So one is lying on the equator plane, that is the equator plane passes through the z-axis, z is equal to 0 axis. So this will provide you one angular node, and the other 2 are theta is equal to 0 and pi. These are the 2 other nodes which will be obtained from the sine square theta is equal to 0 lying along the z-axis, whereas the density peak, that is the value of the density, will be maximum. That value will occur at theta is equal to 54.7 degree and at theta is equal to 127.3 degrees. So 54.7 degree is the angle corresponding to these 2 lobes, and theta is equal to 125 degree is corresponding to these 2 lobes. Okay. So you see that, and the orbitals, that is the molecular orbitals, then can be constructed using this type of simple orbital will be Fz times x square minus y square, and f of x, y, z orbitals can be constructed. Now I am going to move to the next orbital, which is P3 minus 2. So it will have a similar description, only the magnitudes will be different. Here the magnitude is equal to 6. That is the wave function is restricted within this within a radius equal to 6 units. But when we talk about the next one, which is the case of L is equal to 3 and P is equal to and M is equal to minus 2, that is the magnetic quantum number has value equal to minus 2, you will see that this picture is identical to the previous one, but only the magnitude. Notice the magnitude is 0.05, which is much smaller. How much smaller is this? The rest of the things are the same. That is the density, that is the maximum of the density will occur at the same angles that I have discussed previously. The number of nodes, the number of angular nodes will also be identical, 3 in the number. This is what I have discussed in the previous slides. So all the knowledge of the previous slides will be applicable to this slide, except that we can say the values are scaled down by a factor of 1/20 relative to P32 case. The probability density is also the same, and the absolute square of y3 minus 2 and the absolute square of y32 will be the same, because this will be taken care by the normalization constants. So the probability of finding the electron will be the same in the 2 cases, that is for the P3 plus 2 case and for the P3 minus 2 case. There are 3 angular nodes as for the previous case, one at the equator and the other at 0 and pi. And you see that the description, as I told you, will be similar and exactly the same as that of the previous case, but only the magnitude of the magnitude that the wave function is restricted is different. So here the magnitude is equal to 0.05 radius unit. The next one I am going to discuss is P33. So if you plot the wave function, if you plot the associated Legendre polynomial corresponding to P33, that is for L is equal to 3 and M is equal to plus 3, you will find this wave function. So P33 as a function of cos of theta is equal to minus 15 into sine theta to the power 3. And the orbitals that can the molecular orbitals that can be constructed using this associated polynomial, Legendre polynomial, are fx times x square minus 3y square, or fy times 3x square minus y square. These f orbitals can be constructed using the associated polynomial of P33. So you can see the picture. And let me, if the three-dimensional picture is also shown, another version of the three-dimensional picture for a continuous wave function going from 0 to 2 pi, the value of phi going from 0 to 2 pi is also shown below. And this is a discrete picture taken showing you a different lobes, 6 type of lobes, that is 3 pair of lobes is also shown in the middle. So let me go through it. It is a 2-lobe structure, dumbbell-like in 2D, as shown in the polar coordinate system, in the polar picture, flattened along the z-axis. So it is a flat structure along the z-axis and concentrated entirely at the equator plane in the form of a torus or in the form of a ring shape, as far as the three-dimensional picture is concerned. The maximum probability is found exactly at the equator, that is on the xy plane. You can find out the maximum probability as shown as evident from this torus shape. That is the probability on the xy plane. The xy plane is equally probable. So the probability at all points around the xy plane is almost the same, but only varies with the distance from the center. So if you move away from the distance of the center, the probability will vary, but of course it is uniformly located about the center. So the maximum probability is found exactly at the equator. There is only one node at an angle of 0 and pi, and this node is actually mathematically, this node is occurring 3 times because we have sine to the power 3. So mathematically this node is occurring 3 times. So these are actually 3 nodes, or you can say that one node, that 3 nodes are you know that the same repeating themselves. So repeated nodes, and the value of the node is theta is equal to 0 or pi degree. As m increases from 0 to 3, electron density migrates from poles towards the equator. You can see from the previous 3 cases. For example, this case, the electron density is located along the z-axis. You can see. But now it is deviating from the z-axis. It is further deviating from the z-axis in these 2 pictures. And now it is on the xy plane. So that's why we have said that as m increases from 0 to 3, electron density migrates from the poles, that's from z-axis, towards the equator, that is on the xy plane. The next one is, the next case will be Since we are reducing this case as the P33 case, the next one will be P3 minus 3 case, where the magnetic quantum number will be equal to -3. Here you can notice that the magnitude where the wave function is constrained to lie has a value of radius equal to 15 units. But in the next case, which is the P3 minus 3 case, you will notice that there will be a decrease in the magnitudes, which is equal to, and the magnitude and the wave function will be lying in a radius of 0.02 units. So this is a very small region in which the wave function is constrained. The rest of the pictures would be the same. The rest of the discussion is also the same. The number of nodes in probability densities is also the same. Only the magnitudes where the wave function was restricted was different from the previous case. So like m is equal to 3, this produces a flattened two-lobed shape. Density is concentrated at the equator, that is at 90 degree or 270 degree, or pi by 2 or 3 pi by 2, or on the xy plane, because the equator plane is the xy plane, and on the whole plane the density is the same, because the shape is in the form of an of a torus or donut that we have discussed, where it indicates that around the value of z-axis the density is the same all around about the z-axis. The electron density is pushed away from the z-axis, but of course, as in comparison with the previous cases, that is with m is equal to 2 case, m is equal to 1 case, m is equal to 0 case, we have seen that with greater value of m, the density is pushed away from the pole towards the equator, and here this is the case of equator again. There are nodes at the poles. You see that the number of nodes will be the same, and this node is repeating nodes occurring three times, but the value of the node is the same, because the wave function contains a value sine of theta raised to the power 3. So there will be 3 repeated nodes. The structure is scaled by 1 over 720 relative to m is equal to 3 case. The probability density is the same for the two cases. That is the absolute square of y3 minus 3, and the absolute square of y3 will be the same, because it is taken care of the normalization constants associated with the spherical harmonics. So you see that this is a summary that I have already discussed. While discussing m is equal to 0 case, m is equal to plus minus 1 case, m is equal to plus minus 2 case, and m is equal to while discussing m is equal to plus minus this case, along with the l is equal to 3, I have also discussed these things while discussing all these figures individually. So you see that in this lecture I have discussed different orbitals starting from L is equal to 0, m is equal to 0, to all the way along m is equal to 3, and all the 3 cases associated with m is equal to, with L is equal to 3. You see that there are how many cases are associated? 7 cases are associated with L is equal to 3. M is equal to 0, 1 case. M is equal to plus minus 2, 3 cases. M is equal to plus minus 2, now 5 cases, and M is equal to plus minus 3. So this total becomes 7 cases. So we have this case discussed L is equal to 0, L is equal to 1, L is equal to 2, L is equal to 3, and all the possible values of M have been discussed. The shape of the orbitals have been discussed. The maximum value of probabilities have been discussed. The overall probability densities have been discussed. The number of nodes have been discussed. So all these discussed, and the wave function, the value of the wave function, the constraints on the value of the wave function have also been discussed in much greater detail in this lecture. I hope this lecture would be useful for you. So this is the end of slide number 9B of the course on atomic and molecular physics.